7.4, reactions in solutions. Today we're really going to focus simply on double replacement reactions and how they actually behave when these things occur. The first thing we want to do is to talk about what actually happens to a solid as it dissolves in water. And I showed an equation like this today in class, but I want to get a little bit more in depth with it in today's notes. When an ionic solid is dissolved in water, its ions are going to tend to break away from one another. If the water molecule is stronger than the bond essentially between the two ions, the water molecule will actually pull those ions apart. There's two terms that we use to discuss this process. The first term is called ionization, and the second term is called dissociation. If you dissociate from something, you remove yourself from something, or you take yourself away from something. So that term is a very frequently used term, and it gives us a nice visual of this process. Let's take a look at an image that kind of shows this idea. We've got sodium chloride. Sodium is being highlighted by the blue spheres in the picture. The chlorine is the orange large sphere in the picture. Chlorine ions are larger than sodium ions. And then the green-purple things that are kind of floating around, those are the water molecules. And I like this image because it really shows the water molecule attacking the salt crystal and pulling everything apart. And you can see that we have dissociation going on because eventually the blue and the orange molecules aren't hanging around with each other anymore. The process that we have here in the image can be highlighted by writing a special equation. And we call this thing a dissociation equation. So let's take a look at what a dissociation equation looks like. We don't call these things chemical equations because it's actually not a chemical process that's actually occurring. All right, so we're going to look at a compound, calcium bromide. So CaBr2. It's a solid, so let's put down the phase. And if we put that stuff into water, if we dissolve the stuff into water, we're going to get a dissociation to occur because this material is soluble in water. But as a solid, as I have here in my picture, we can see that the calcium and the bromines are kind of attached to one another. So they're latched on to each other essentially, and they're not broken apart. So that's what I'm trying to draw with these blue lines that I have on that image that are between the calcium and the bromines, is that they're attached, they're connected. All right, so let's go ahead and do a dissociation. So we're going to add some water to the solid. And when this occurs, the water is going to be strong enough to essentially pull apart the ions. So the calcium is going to come off. It's going to kind of behave by itself. The bromine is also going to come off, and it's going to behave by itself. Now, one of the big things about this is to know, well, what's the ratio of like cation to anion? And if we look at our beginning material, our solid material in blue on the far left, we'll notice that we have a 2 subscript for bromine. Well, that means we need to have 2 bromine ions for every 1 calcium. So I actually have to balance this dissociation equation just like I have to balance a chemical equation. Now let's think about what's happening inside of our beaker when the water is added. So here's my beaker again. And now instead of the calcium and the bromine actually being attached to one another, we have calcium ions that are floating around in solution. And they're totally independent. And they're totally independent of the bromine ions that are floating around in solution. But one thing to note is that there needs to be twice as many bromines as there are calciums because of the stoichiometry involved, because of the coefficients that are involved in the chemical equation. So now when this stuff is sitting here in the water, dissolved in the water, we actually have an image that looks more like this one than the one on the left. All right. So that's the premise of a dissociation equation and the way that we want to represent the dissolving of solids. Now, let's say, for instance, we take 2 of those solutions and we combine them. Well, that's what a double replacement reaction is, in essence. But the way that we've been writing double replacement reactions has kind of been, well, we've kind of been cheating. We've been writing a double replacement reaction by taking the reactant species, the stuff on the left side of the yield zero, and kind of squishing them together. And then after that formula, like NaCl for sodium chloride, we write AQ for aqueous. However, that's not exactly what happens because NaCl is not squished together. The sodium is totally independent of the chlorine. They're apart from one another. So we're going to use these things called complete ionic equations that will show the true story of an aqueous equation. And the main thing about a complete ionic equation is that the aqueous species aren't really combined. So if we look on the bottom of the page here, I've got an example of a double replacement reaction. And you can see that the species on the left side of the yield zero aren't combined. So even though we write AgNO3 and we kind of squish it together, if we were to look in the beaker, there is no combined AgNO3. There's some Ag and there's some NO3, but they're independent of one another, as independent as the sand and the rocks that are on the beach. They're not combined. The same thing can be said for the NaCl. The Na is independent of the Cl. In fact, in this particular chemical reaction, the only time in which the ions are actually attached to each other is when the precipitate is formed, in this case, silver chloride. There's still stuff on the product side of our yield zero that is non-combined. The sodium and the nitrate still float around in solution uncombined. All right, so how can we better represent this process? Like I said, we've been kind of cheating with our chemical reactions. So is there a better way to represent this process with our methods? And actually there is. So let me open up a sample. All right. And let's take a look at this process. Now we're going to go with silver nitrate again. So similar to what I had on the previous slide. But this time, instead of squishing the silver and the nitrate together, I'm actually going to start with them broken apart. So the silver is in its ion form. So it's got a plus charge, it's aqueous. The nitrate is in its ion form. It's got a negative charge, it's aqueous. And we're going to combine the silver and the nitrate ions with two other ions, magnesium ions and chloride ions. Now I want you to notice something about the Cl in this case. We've got Mg2 plus 2Cl minus. Where does this 2 come from? Well, we've got MgCl2. That's the formula for magnesium chloride. And when I broke this apart, because it was dissolved into water, for every one magnesium ion I have 2 chloride ions. That's what the subscript is telling me again. All right. So let's just take a look as to what we would get on the opposite side then of our yield zero. We get AgCl. That's the actual precipitate that's formed. And so again, I can squish the Ag and the Cl together because literally those ions are squished together inside of the beaker. But I still have other ions that are not squished together, that are still free floating in the beaker. In this case, it's the magnesium, the red stuff, and the nitrate, the orange stuff, that I had on the reactant side of my chemical equation. So we can think of the silver and the nitrate as being the stuff in a beaker. Let's call it beaker 1. The magnesium and the chloride being in a separate beaker, beaker 2. And in both beaker 1 and beaker 2, there is no precipitate. It's just two different solutions. But when we mix them, we get all of the things on the right side of the yield zero into a third beaker. And in beaker number 3, we actually see that there is a precipitate on the bottom of the beaker. That is the silver chloride. So what you see right here, ladies and gentlemen, the big, gory, ugly equation that I have up here with all the different colors, that is what we call a complete ionic equation. Remember I said on the previous slide, a complete ionic equation shows the true story of an aqueous reaction? Well, the complete ionic equation is right there. Now, I wouldn't ask you to write beaker number 1, beaker number 2, beaker number 3, but you should be able to write a complete ionic equation for these double replacement reactions. Let me go back there for a second. All right. So let's take a visual of what this looks like. By the way, I just added some 2's in. You see 2's with arrows in front of the Ag, in front of the AgCl to correctly balance this thing. Remember, conservation of mass is really important. All right. So, again, my product would look like this. I'd have some AgCl on the bottom of my beaker. And then throughout the solution, I'd still have magnesium ions that are floating in there, and I have nitrate ions that are floating in there. I might recall some past knowledge and ask you, do you think this solution, if I put some electrodes in here, do you think this solution would be conductive. If I put some electrodes in here and then I hook those electrodes up to, oh, I don't know, maybe a light bulb, would the light bulb glow? And hopefully you would say, well, yes, it would glow, because there are ions in solution. An ion in this solution, and the ions, magnesium and nitrate, would be conductive, and they would allow the light bulb to glow. Right. Now, these two things, these two ions that would allow the light bulb to glow, the two ions that do not combine to form the precipitate, they actually have a special name. They are called spectator ions. And I love that name, because they're just watching. They're not forming anything new. They're not participating in the game. They're just watching. They are the spectator ions. The other stuff, the AgCl on the bottom, well, that's our precipitate. So there's a third way to write this process. We've got a regular chemical equation like we've been cheating with thus far. We have a complete ionic equation like I just showed you above. And then we have an abbreviated way to write this particular process. And that's as follows. We can write just the spectator ions and the precipitate. Because, I'm sorry, we can write just the important ions and the precipitate, not the spectator ions. Because the spectator ions really don't do anything. They don't participate in the reaction. So we don't have to put them in our chemical equation. So this equation that I have here, that I'm going to outline in blue, is what I would call the net ionic equation. It is the net ionic equation because it is the equation that only involves the net particles that actually participate in the process. Okay? All right. So that's 7.4, reactions and solutions. Tomorrow we're going to go through our lab, get some nice visuals of some precipitates forming, and hopefully get a better understanding as to how to develop complete ionic and net ionic equations.